Welcome to Industrial PLC Applications. This video is a part of the First Look series. This video in particular is on single bit instructions, part 3, other single bit instructions. When the PLC scans the inputs and outputs and solves the logic, it does so in an incredibly short period of time, usually a few milliseconds for smaller programs. During this time, the actual change of state period can be longer than the scan time. This means that some instructions will repeatedly act as if they see a change each scan. The PLC can examine the state of any input or internal variable in a number of different ways. It can verify the status of the variable, no change versus new value, acknowledge a change of state from low to high, acknowledge a change of state from high to low, or measure the duration of change. Since the logic scan of the PLC can be faster than some inputs' change of state, you may get unintended logic resolution. Consider below. A push and release of a push button seems like an instant to us, but to the PLC, it may see the input high for many scans, like the 8 scans shown. In this case, you may only care about the change of state, not the duration. That is, did the input change from low to high, or did the input change from high to low? Before we get too deep into the subject, there's some equivalent terms that are bandied about that you must understand mean the same thing. Low to high, 0 to 1, false to true, talks about a change in state from being off to on. All of these are equivalents. High to low, 1 to 0, true to false, talk about the change of state going from on to off. All of these are equivalent. And just to make things more confusing, they are often mixed. Oh, it was on and then it went low. It was 0, but now it's off. It's on now. They interchange them. So just be aware we're all talking about the same thing. It's just an argument in semantics. Rising edge is the term that refers to the instant a false to true transition takes place. It's also known as the leading edge. In many binary cases, it's not just the value of the variable, but the instant it changes its state. When examining a variable for a change from false to true, you want the rising or leading edge, the moment of transition. The instruction to use here is the rising edge pulse contact instruction. To demonstrate this concept of rising edge versus falling edge or duration, we're going to use a standard XIC instruction, and I'm going to trigger it with the simulator. Now, I grant you that the simulator, there's timing issues with it, but this will give you an idea of what's going on. So here we have an add instruction, which is going to add 1 to a variable called scan count. The scan count starts off at 0, and as it adds 1, is going to place the finished addition back into scan count. So every time this is triggered, as fast as I can turn it off and on, it's going to count 1. So watch the result of our scan count. As fast as I can click that on and off, you can see that our scan count is just ballooned because it is counting these every single time you scan, and this rung is true. It says, okay, the rung is true, I got to count 1. Oh, another scan, the rung is true, because we scan our inputs, solve our logic, and then set our outputs. And that's happening on a very quick basis. Part of it has to do with the fact that it's a very small program. So what I'm going to do is I'm going to disconnect, and I'm going to change this trigger to a different instruction. And I do that just by scrolling through. So that would be our examine if off. And we have one that has the letter P. And if we're not sure, we can go up to the top, go to our bits, and say, okay, which one of these bits do I want? And that says pulse rising edge. So we only want to look at the transition from low to high or false to true. That's just that transition, instantaneous moment. That's all we're interested in. And I'm going to download the changed program, and it should reset my scan counts. Download. Just about there. Okay, so now we have the same thing again. So I'm going to bring back my simulator, and I'm going to turn this bit on, and it only counted one. Now I'm leaving that on. We don't know how many scans, whereas before it was just rifling through. So we'll turn it off, and each time I'm toggling this, it's only adding it once because it's looking at that false to true transition, just that transmission point, doesn't care about anything else. Now there can be a situation where you don't need the leading edge, and for that there's a different instruction, and that we're going to change that in the next video. Imagine a situation where you want something to occur the instant something turns off. Say when one pump motor or contactor turns off and you need to energize the backup pump the instant that happens. For this, you use the XIF instruction. This instruction looks for a falling or trailing edge to occur before being true. Falling edge is the term dealing with the moment there is a true to false transition. It's also known as the trailing edge. Alright, in this case we've replaced our pulse to the N, which is the watch for a falling transition, and we're going to put it into run mode. So that's pulse falling edge as opposed to pulse rising edge. And when we watch our count, again it resets to 0, and I'm going to turn this on. It ignores it. I'm going to let it turn off. And you can see how the name actually changed state, but the contact did not. So now it's energized, and you can see it's now energized. This has not changed. I turn it off, and now it counts. So it's counting on that true to false transition. There are quite a few other instructions that work in this fashion, both the false to true transition and the true to false transition. They will not react until they see this change of state. Counters, for example, will normally use the false to true transition, and it won't even examine that until that input has gone from true to false again. It's reset to the false because it's only counting that false to true transition. Now there are times when you may want an output to do something for only a single scan, and that's coming up. There are times you do not want the PLC to mistake your intention by scanning an output for more than a single scan. For these scenarios, you use either the rising edge pulsed output or the falling edge pulsed output instructions. The original aim was one shot. These are one shot outputs. They are energized or de-energized for only a single scan. Alright, so we have a situation where we have a stop button and it's triggering our pulse. We want to count how many times the stop button has been reset. So I energize our DI03, and you can see the output does not look like it's energized. It should factually be true because we have a path of continuity, but it's already energized and changed the stop trigger in what? So I'm going to turn this off, so it's going to go, it's now true. I'm going to make it false, and our count is at 3. And even though this is staying on, the output is not. In truth, if this was a regular output, it would be stayed energized, and again you would see that adding and adding and adding every single scan. But it recognizes it as being a single execution of that output. The same applies for the negative or falling pulse. If you want something to count the opposite, how often is that stop button being pressed? Maybe there's something wrong with it. There could be a loose wire, it's bouncing, and you want to see, okay, how many times is this happening that's causing us to have to restart? So those two instructions are often used. It's the replacement if you can't look at an input or you're working with a particular output. For example, you want to see that your counter's working properly. You could parallel one of these with a push button that is being used to count, and the two counts should always agree, and if they don't, then something might be, you might have a loose wire, or maybe you're hitting the switch and it's getting a double pulse, etc. But they're often quite used to make sure that something happens at the same time. So if you want to send a signal out to another PLC, you will pulse it and say, okay, I'm going to send this bit out and it's only going to get sent once. I don't want to keep filling my buffer up with too much information, etc. Normally, to turn off an output, we simply interrupt the logical path of continuity, like opening a motor circuit by pressing a stop push button. But what if you want to shut something down as a precaution, or because an unusual set of circumstances has occurred? For that, we use the output off coil or reverse coil. This instruction begins by energizing a variable, and then when the logical continuity is met, it turns the output off. This may sound counterintuitive. We don't normally think in terms of on, then off, but we can use it for fail-safe operations. Okay, so we can see in our program here, we have this NOT coil, this OTO, is currently energized, and yet there is no logical continuity. It should not be energized. This is its normal state, and we're calling it pump permissive. And in our first run, we have an instruction that says run, and the pump permissive says, yep, go ahead and run, and the pump is now running. So perhaps, especially if you're filling tanks, etc., you don't want the tank to overflow. You don't want too much stuff. Tanks are not designed to be filled right to the top, for example. So you're likely going to have some sort of a float or a level mechanism to determine it. So in this case, we have a float switch, and every time the float switch is made, because it can be bouncing due to turbulence, you want to count how many times, and if it bounces too many times, you want to shut the pump off to figure out what's going on. Why is there so much turbulence? Why is it, making and breaking so quickly? So we've got here a trigger, stop trigger, and it's a pulse one-shot instruction, and I'm just going to toggle the pump float, and we can see our pulse is it's not staying, so it's not triggering, and we get up a little bit more. We're up to now 12, so if it bounces a couple more times, and now the run permissive is taken away and the pump shuts off. So this instruction is handy to use for a fail-safe operation. something that you would normally allow it to happen, but if a certain set of conditions occur that is unexpected, you have this way of saying, okay, I'm opening up the circuit because this is not normal. As you can see, there are numerous instructions that work on a single bit, each designed to address a particular situation or monitor only a change in state as opposed to simply working with the change value. In a future video, we're going to see how we can use a multi-bit instruction to control individual bits. Until then, thanks for watching.